Okay, class, we're ready for our last experiment, and we will be using the same formula. We will be doing an experiment with the third order lever. So if you look there at the bottom of your page, you should see the experiment with the fisherman, and he is lifting using a fishing pole as a lever. So we're going to take a look at this one, and then this will be the last experiment video, and there'll be one short notes video after this one. Okay, just to give you a few points because we're going to notice something at the end of this experiment. So the first thing that we need to do is, you see I have it all set up behind me. I have the load weight at the end, okay, of my board, just like he has the boot there at the end of his lever. And we will, if you notice right here over my shoulder, there is a little silver hook, and that is where we will be pulling. So that's where we'll be putting our effort in. And I have wired the end down there to the fulcrum just to keep it from lifting on me. So everything's all set up and ready to go. We just need to do our math and then see if we can't prove our science with our math and our math with our science. So let's take a look here. First thing we need to do is we need to fill in our DL and our DE. Our DL is the distance to the load, so that's from our fulcrum the whole way down to our bucket. And we know the length of our board from our last experiment, and so our DL from the fulcrum to the load is 8, right? It is 8 feet. So we can go ahead and fill that one in. Now we need to measure the distance from the fulcrum to where the effort force is. So we're going to measure to that little silver thing right there. So we'll need our tape measure, and we're going to measure the distance to the effort, the DE. And there you can see it is 4 feet. Okay? So we are going to be pulling up on it right smack in the middle. Okay? So we can go ahead and fill in the DE, and that is 4. Okay? Alright, so we've got our DL and our DE filled in, and the next thing in our box there is R, and R is the mass of our object, and we do know that we had 4.5 kilograms when we weighed our bucket, right? The last time we had to take into account the whole board because we were lifting on the end. So before we write in our R, my question is, how much of the board am I lifting if my pull point is in the center? I'm lifting from the center. How much of the board am I lifting? When I lifted from the end, I lifted the whole board. If I pull from the center, how much of my board will I be lifting? If you said half, you're correct. Yes, it is half, right? And that is because this end of the board will be lifting, but that end of the board will still be resting on the fulcrum. We're not going to be lifting it off the fulcrum. So it's not like when we took the mass of our board and we hooked the pull scale to the middle of it and we weighed it by hanging the whole board. That end of the board on the fulcrum will not be being lifted up off the fulcrum. So if you said half, you're correct. We're only going to be lifting and pulling half of it up, okay? And yes, if you remember that when we did take the mass off our board, it was 4. So half of 4 is 2. That is a pretty easy calculation to do. We can do that in our head. So half of 4 is 2. And now we know we have 2 kilograms of board weight, right? Half of the board is what we're lifting. Half of 4 is 2, so we have 2 kilograms of board weight to lift. And we have 4.5 kilograms of load weight to lift. So if our bucket is 4.5 and half of our board weight equals 2, then we can come up with a total weight, total R of 6.5. So 4.5 plus 2 is 6.5. Okay? So go ahead and fill in 6.5 beside your R. Now, it looks like we have our DO, our DE, and our R all figured out, which means we can plug these into our formula pretty simply. DL is 8, DE is 4, our R is 6.5, okay? And that math is a little bit easier. You might even be able to do it in your head, but we'll go ahead and do it on our calculator just for the sake of doing it, being consistent. So we can say 8 divided by 4 equals 2 times 6.5 equals 13. So what our pull scale should read when we hook it to that the center of the board, that 4-foot point, okay, what our pull scale should read when we hook it right there and lift up is right around 13. Okay, so that's what we're looking for. Now, it's very interesting for us to note that 13 is more than 4.5. So let's talk about that after we see it, if our science will prove our math. Okay, let's take a look and see if we can get it to be about the same. Make sure it's 0. It is. Charm, right? And our number is 12.88, which rounds nicely up to 13. So we can go ahead and fill in our box there with F being 13, and we are really close. So we can see that our science is matching our math, and our math is matching our science. Now, to have a little bit of discussion on why it took 13 pounds, that definitely isn't a mechanical advantage, is it? Like, so it took me 13 pounds of effort to lift something that was 4.5 pounds. Well, the big thing that you gain from a third order lever is distance, okay? So it isn't necessarily less effort, it is that you are able to cover more distance. When I lifted from the center of the board, I only lifted about that far. Yep, but my bucket went about that far, okay? It went from here, clear up to here where it was about level. Okay, so it is called a distance magnifier. Okay, it is helping you gain distance. It is making the effort or the effort you're putting in greater, but the distance that you're pulling the load is much greater than the distance that you're moving. So it's called a distance magnifier. And you'll see that in the next short video that talks a little bit about just the first and second order levers, the things that you need to remember, and then the things that you need to remember about the third order lever. So you'll find one of those boxes on your note sheet, and one of those boxes is here on the bottom of your experiment sheet. So get both of those sheets together for the next video that is going to review those two things for you. Okay?